All right, we're going to look at power. I'm going to talk about two types of power today. We're going to talk about instantaneous power. That occurs at a single point in time, and average power. This occurs over an extended period of time. So when do I use which? Well, I use average power if something is occurring, like I'm lifting a can from the ground to the top of a shelf. It took some time to do that. I look for instantaneous power if I know there's some sort of velocity, and I want to find the power to maintain a velocity. Think about your car moving in cruise control. How much power is required to overcome that air resistance to go 70 miles an hour? So here we go. Instantaneous power is equal to the force dot the velocity. What that really means for us is we want the parallel component of the force times the velocity. So in our case here, I have an example of a motor hoisting up 400 kilograms of bricks straight up at a constant velocity of 0.75 meters per second. So the first thing I need to do is I need to find out what force is the motor supplying. So what's the tension in that string? So I would start with my free body diagram. So I have a couple forces acting on here. I have the tension and I have gravity. Now because I did use the word constant velocity, we know that these two forces must add up to 0. So I can say that tension minus mg equals 0 when I add up the forces in the y direction because it is moving at a constant velocity. So the tension is equal to mg, so I do know my force being applied by my motor. So my power is going to be mg times how fast we're going, v. Now notice that the tension and v are in the same direction, so I don't have to find any components of the forces. Okay. Next, I'm going to plug in my values, so I have 400 times 9.8 times my speed of 0.75. That gives me a power output of 2,940 watts. Easy way to remember that? Watts of power. Okay, so we have 2,940 watts. Now we also use horsepower from time to time, so we do need a conversion factor that 746 watts is 1 horsepower. So if I do convert this to horsepower, the power for this motor to maintain this speed as it hoists it up is 3.94 horsepower. Okay. Now that isn't by any means the maximum that motor needs, but that is the force it needs to maintain this speed for this load. All right. Let's move on to average power. So this occurs over a period of time. So I have a student stocking a shelf at the local grocery store. They have 30 cans per minute that they can put up on the shelf, and the shelf is 2 meters high. This is top shelf quality stuff they got. And each can is 500 grams, so 0.5 kilograms. And I want to find what is their average power as they move all 30 cans in 1 minute. So in order to figure this out, I first need to find out how much work does a student do in lifting 30 cans up to that height. So I think about that work kinetic energy theorem we did earlier. So I have the work in plus the work done by friction equals K2 minus K1 plus UG2 minus UG1 plus there's no springs. So I start crossing stuff out. For instance, there's no air resistance really to speak of slowing down that can. The kinetic energy is 0 at both the start and the end because the can is stopped here, and when we leave it on the shelf, it's also stopped. We're not throwing the cans up in the air. Okay, we're setting them on the shelf. And then lastly, the initial gravitational potential energy is 0 because it starts at a height of 0. So that means that the work in is going to be equal to the final potential energy, mgh, for the cans. So the power is going to be mgh divided by t, the time it takes. And so we got to find the total mass. Well, if they lifted 30 cans at 0.5 kilograms per can, you guessed it, that's 15 kilograms times 9.8 onto a 2-meter high shelf, all divided by a time of 1 minute. So I'm going to use 60 seconds because watts is joules per second. So I get my power, and it turns out that our stock worker is operating at 4.9 watts on average during this process. Not watts of power. All right.